Guys, this is the Academic Chemistry, Chapter 6, the Periodic Table, Part 1. So today we're just going to talk about the history of the periodic table and kind of how it's structured. Now you've already used the periodic table quite a bit, so you know some of the tricks to it, but now we're going to go into a little more detail. So first, let's take a moment just to admire the beauty of the periodic table. I mean, that structure is perfect. Now, sometimes students say, why is the periodic table so complicated? There's all these columns and groups. And the thing is, it's actually complicated to make your life easier. And once you understand how to use it, it's not actually complicated at all. It's actually super easy. And you're going to be like, oh my gosh, old dudes that made this periodic table, thank you. So let's talk about who those old dudes are exactly and give them the respect they deserve. All right, so the first guy we're going to talk about is Lavoisier. He was from France, and this is back in 1790. He made a list of all elements that were known at the time, and there were 23. Let's just take a moment to think about that. You probably have a class that has 23 or more students. That's all they knew. They knew like oxygen was out there and hydrogen, but they had no clue about metals, maybe like cadmium or something. No idea that they were there. They knew stuff was there. Maybe they thought it was a compound, or maybe they hadn't even discovered it yet, which is super cool because that really wasn't that long ago. So once the Industrial Revolution started, there was a lot of science happening. So they found lots of new elements really quickly once the Industrial Revolution happened. The next guy we want to talk about is 1864. So that really wasn't that long ago. I mean, what, 150 years ago, roughly? And we've got John Newland over in England. And what John Newland noticed is there were patterns of periodicity. So every 8 elements, there were these patterns he would see. So increasing atomic mass, similar properties. All right. Now he called these octaves, which I love as someone who did music. So an octave is 8 notes, right? So he noticed this periodic pattern. Periodic means keeps recycling over and over, that if you arrange stuff in increasing atomic mass, these properties continuously occurred every 8 elements. It didn't work for the whole periodic table once more things were developed, but at the beginning, that was a pretty cool way of thinking. Like, whoa, some things happen to have similar characteristics. And for what he knew, it was every 8 elements, so we called them an octave. Okay, not too long after, 1869, Dmitri Mendeleev in Russia and Lothar Meyer in Germany both came up with the same concept of how to organize elements. Now, generally, Mendeleev gets most of the credit. I think it's partially because Mendeleev has like a crazy story. So he had a ton of siblings. He was in Russia, his father passed away, and his mom was like, I can't do it, and she just dropped him off at a university, like as a child. And so the university took him in, and he had nothing but university, so all he did was study. And then he was an old grouchy professor, and he couldn't understand why his students weren't able to just memorize all the elements like he had. Hello, he'd been studying since he was a child. But he listed all the elements in increasing mass. Now we have a little bit more elements now, and he noticed this regular pattern of periodic or reoccurrence of physical and chemical properties. And the way he organized it looked a lot more like a periodic table than our previous one. And he had just organized note cards to try and make it easier for his students. And then he was like, oh, snap, look at when I organize, I can make this beautiful table. So he made the first like real periodic table, but this was by increasing atomic mass. So that's the total number of protons and neutrons. And if we remember back from chapter 4, you can have different numbers of neutrons in the atom. So sometimes the atomic mass changes, which makes the periodic table, if it's organized by atomic mass, not really consistent, because every element doesn't have one set atomic mass. It might have different because there are different isotopes. So Mendeleev's chart listed those elements with similar properties side by side and increasing mass from top to bottom. So here's a little picture so you can see how it's kind of similar to what we have. Several of the elements we know today hadn't been discovered yet. But using Mendeleev's chart and organizing them not just by mass, but also by properties, he was able to leave open spots. He said, well, if element this has this property an element, this has this property, they can't be in the same column, so there must be something missing here. And that's actually, he was able to predict gallium 15 years before it was discovered. He could say it's going to have this mass on average, it's going to have these properties, and it's got to be out there because that makes sense for nature, which is really cool. Like, that's what made Mendeleev, be the winner of the prize of who gets the most credit for the first periodic table. But then in 1913, so just 100 years ago, approximately, Henry Moseley, he was in England, and he proved that the atomic number instead of the atomic mass should be used. Now, this kept a lot of the elements in a similar order, just some of them flipped around. So like Mendeleev, he was able to predict a bunch of elements that hadn't been discovered yet. Because again, we're organizing things based on properties, and you can see holes. Like if you know that there's something with 7 protons, atomic mass, right? Protons, 8 protons, 9 protons. If you don't have something with 10, they didn't have 10 discovered, but let's say they didn't. But you have 11, you can assume that there's something with 10 protons out there. The cool part is that they could tell what the properties were without discovering it. So for today's known elements, it all fits on this periodic table that Moseley discovered or arranged just 100 years ago. So we currently have 118 known elements, things that we have discovered, we have isolated, gotten down to the atomic level to be pure elements. Pretty awesome. Like, just 4 of them or so were added within the last couple years because we're still making discoveries. Around 30 of the most commonly used elements are on the periodic table. So out of those 118, 30 of them approximately are the ones you really interact with every day. I'm talking oxygen, so that's what you breathe in, right? Carbon, you are carbon-based life, so your body is mostly made of carbon. We've got hydrogen in the air, nitrogen, right? 73% of what you're breathing in, it depends on the area, it could be 77%. It's just pure nitrogen in the air. So there are some that we come into contact with all the time, and then there's some rare ones. Like you're probably not going to see any francium. Francium's like way down deep in the core of the earth, so you're not going to check that out. But helium, you're going to see pretty common. Over 20 of the elements on our periodic table are man-made, or we call them synthetic elements, meaning we actually take smaller elements and smush them together to make a larger atom, and we see how long it'll last. Some of them only last very, very quickly before they break down into other elements through nuclear decay, so through nuclear radiation. But that's pretty cool that we're actually able to make atoms out of other atoms, like smush them together, and that's particle physics right there. So if you ever study that in college, you're going to learn some really cool, funky science out in the world. So if you're looking at the periodic table, here is one. There are a few main terms that you need to know to be able to talk about the organization of the periodic table. And let's start with periods. Periods are horizontal rows, so from left to right on the periodic table. Groups are vertical. So like when you stand up with your group, you're standing up and down, right? Okay, so up and down are groups. So elements in the same group have similar chemical and physical properties. The reason for this, and we learned this back when we were doing electron configuration, is all the elements in the same group have the same number of valence electrons, and those are the electrons that are doing bonding. So anything like lithium, sodium, potassium, rubidium, those all have 1 valence electron. So they're all going to do things that an atom with 1 valence electron would do. These all have 1, these have 2, so these act similarly. A lot of these have 2, we go, so it's 1, 2, 2-ish. These all have 3 valence electrons. These all have 4, carbon down. Nitrogen down has 5, oxygen and down have 6, fluorine and down have 7. Remember, neon and down have 8, except for helium's funky with 2. So if you have a certain number of valence electrons, you're going to act like anyone else with those valence electrons. So carbon and silicon both have 4 valence electrons. Now, I said earlier that you are carbon-based. So your body is built off of carbon molecules or organic molecules. Organic molecules are mainly carbon with oxygens and hydrogens attached. And that's what any kind of living matter is made out of. So carbon and silicon are really similar, just silicon's bigger because it has an extra shell of electrons, right? It has electrons in that third energy level. So if you read some science fiction book, though, they might talk about like silicon-based life. It's not a real thing. But the reason they talk about silicon as potentially being something that could have life is because carbon makes all these cool bonds because it has 4 electrons, valence electrons. Well, so does silicon. So since silicon has 4 valence electrons, in the sci-fi world, they theorized this world that could be silicon-based. Silicon's actually way too big and bulky because it has that third energy level that it's not going to be the basis of life, but it's kind of cool to think about it because elements in the same group have similar properties. So maybe on some planet we discover someday there'll be silicon-based life, but so far, no luck. All right, so again, groups are up and down, and periods are left to right. So let's talk about what makes up the periodic table. So there are 3 main regions of the periodic table. There are metals, nonmetals, and metalloids. Let's go through each. So first, what are metals? So here are all the metals of the periodic table. So metals are malleable, which means you can hammer them into shape. They are ductile, you can make them into wires. They are conductive, meaning stuff can flow through them like heat and electricity. They're illustrious, shiny, and they are usually a solid at room temperature. The exception to that is mercury, Hg, which is why mercury used to be used in thermometers because it was metal and it was a liquid, so it could get bigger and smaller. It was also used in teeth filling back in the day. It is no longer because it was a metal, which made it really sturdy, but it was a liquid, so you could fill it into those spots in your tooth that were drilled out when you found a cavity. They would put mercury in it and then cover it up with a different metal so it was all locked in. Now, if you notice, most of the periodic table are metals. Most elements out there are metals. If you ever forget which side, the way I like to think about it is I see calcium over here, which makes me think of bones, and it makes me feel like I'm a robot because my bones are really mostly made out of calcium, which is a metal. Anyways, if you forget that, look, you've got your basic ones. Iron, you know that's a metal. Cobalt, nickel, silver, gold. These are all metals, okay? Sodium is a metal. And if you think back to the beginning of the year when we dropped the sodium in the water, the sodium had that silvery color. It was hard. It was shiny. That's a metal. Don't be confused with when things get into a compound and then their properties are no longer observable. So here's some examples. So you have metals, a whole bunch of different metals, and I'll have some examples in the classroom if you come see me and check them out. Here's another example. So we can make them into really cool shapes because they are malleable and ductile. Here's a bunch of just elements. So if you notice, platinum, gold, magnesium, all of these are cool different metals. All right, the next group, nonmetals. These are non-conductive, meaning if you put heat on them, the heat's not going to flow through them. Electricity does not flow through nonmetals. They're usually gases. We breathe in nonmetals, and they're brittle at room temperature, meaning they break very easily. Bromine is the only one that is a liquid at room temperature. So over here, these are our nonmetals. So nonmetals are over on the right-hand side of the periodic table. So we've got sulfur that you guys used that in a lab before. It was yellow, and you could really break it apart and make it into a powder. Bromine, nitrogen, carbon. So if you're writing with a pencil right now, graphite, that is carbon. Also in a different allotrope form, diamonds are actually carbon too. So that's kind of cool to think that those are similar. So here's a few more examples just for you to see. So metalloids are the last little bit. So metalloids are kind of like metals and kind of like nonmetals. So if you think of metalloids, it's kind of like metal-ish, right? A little bit of both. So these are this staircase pattern here. Oh, and if you look, it's over on the right-hand side. So it actually separates all the metals from the nonmetals. That's why it's really cool the way the periodic table looks. Like you're organizing it by increasing atomic number, but at the same time, everything fits together. Like they all work. The metals end up together, the nonmetals end up together, and the ones that are similar to both all end up together as well. If you look at how the metalloids are structured, it starts with boron, and then it goes diagonal. So boron, diagonal, down, over, down, over, down, over. So it only goes one diagonal, and it goes down, right, down, right, down, right. These are all your metalloids. All of them touch. Most periodic tables have this dark stair-step pattern. So all the metalloids, if you notice, touch that pattern. The only one you want to be cautious of is, notice aluminum touches steps but is not a metalloid. Aluminum is a pure metal. So we're touching the staircase, those are all your metalloids. So those have metal and non-metal characteristics. So like if you check these out, these are shiny, but maybe they're brittle, or maybe they don't conduct electricity, but they're still shiny, or they can still make wires. So it just depends on which one. It also depends on who they're bonding with, if they're going to act more like a metal or a non-metal, and we'll get more into that when we talk about bonding of compounds. All right, so there are a few main groups of the periodic table. So over here, our S block and our P block, those are called your representative elements. Why they're called your representative elements is, first of all, they're main deal elements. They all have outer, like, valence electrons. They really do the counting of valence electrons, but mainly they represent all different types. We've got metals over here, metals. Metalloids are represented, and nonmetals. So the S and P block make up your representative metals. The transition metal, I'm sorry, representative elements. The transition metals are your D block and your F block, because it's literally transitioning from metals to nonmetals. Remember, metals are over here on the left, nonmetals are over here on the right. Transition metals exist between where your metals are, and then bloop, we're transitioning over to the non-metal-ish side. Now, it's still touching metals over here, but eventually it's non-metals. On the bottom here, we have intertransition metals. The periodic table technically opens up right here, and the inner transition metals are transition metals. They just squeeze inside to the D block. So the D block opens up, and the F block actually fits in there. But most general chemistry doesn't use the F block elements. They are in a lot more physics equations, like upper physics and really advanced chemistry. So since they're not used as often, we take it out of the periodic table to make it less bulky and just stick them on the bottom. So there's some groups that you need to be aware of, and some periods that have special names. So the first, alkali metals. This group 1 right here, they're called 1A. So if you look at the numbering, 1, 2, 3, 4, 5, okay, that's the normal way of numbering. See how this, it's kind of covered right now, but we have a 1A, a 2A, and then these are all Bs, and then 3A, 4A, 5A, 6A, 7A, 8A. That's the American way of organizing groups, and that's just to quickly tell you how many valence electrons. B, you ignore. If it has a B, it doesn't tell you anything about the number of valence electrons. But if it's an A, you just say, boom, that's how many valence electrons. So all alkali metals have one valence electron. You want to be careful, though. Hydrogen is not a metal. It sometimes acts metallish, but generally we don't classify it as a metal. It's just in its own little thing. So alkali metals are lithium and down. Alkaline earth metals are beryllium and down. So that's the group 2A. So alkali metals always have one valence electron. Alkaline earth metals have two valence electrons. The reason they're called alkali and alkaline is when put in a solution, they make it alkaline or basic. So acids and bases, if this is added, it makes it more basic. Next, we have over here, halogens are very special nonmetals because of how readily they react with things. They're called halogens. And all the way on the right are the noble gases. Now, my high school chemistry teacher, my strongest memory of him is him jumping up onto the lab benches and bowing down to the noble gases because they are elemental royalty. Oh, noble gases, whoa. Because noble gases don't bond with anything else. They're called noble, like they don't interact with the peasants of the rest of the periodic table, and that's because they have a full valence set of electrons. So they all have 8 valence electrons. Notice they're in group 8A, except for helium. Helium has 2. Next thing to know is the lanthanide series. So that's everything in the top period in the inner transition metals. It's called lanthanide because it happens after La, element. All right, and then also we have the actinines, 90 through 103, because they come after AC here. So this is what the periodic table really looks like. Remember I said group D opens up to let the F in. But there are other ways that other people have organized, and these work too as periodic tables. Whoop, didn't mean to go through so fast. So we could have used this, or we could have used this. They work just as good. They're just different ways to look at the periodic table. Personally, I like ours because it's what I've used my whole life, but it's fun to just see what other people use. All right, good luck with the section, and I will see you in the next set of notes.